By the end of the 19th century, many scientists believed physics had almost everything figured out. Light, magnetism, electricity, every known force seemed to fit neatly into a grand, elegant order. The atom, that tiniest building block of reality, was thought to be stable and unchanging. Nothing indicated that hidden inside the atom lay a power capable of piercing solid matter, reshaping it from within. Then came a revolution. In 1895, Wilhelm Röntgen discovered X-rays. Suddenly, invisible energy could blaze through flesh and bone, exposing what the eye could not see. But even then, this phenomenon seemed exotic, dependent on special equipment and controlled experiments. Who could imagine that some elements might, on their own, quietly emit invisible rays, day after day, night after night, with no external trigger? And so it was that a cloudy Paris sky, a forgotten drawer, a simple, failed experiment, and a curious French physicist would conspire to crack open classical physics forever. A revelation that would burn an image onto a photographic plate and ignite a new future for science. How could such a powerful force be discovered by accident? How did a simple mistake reveal one of the universe's deepest secrets, the phenomenon we now call radioactivity? That is the story you are about to witness. The discovery of X-rays by Röntgen in 1895 shattered the comfortable assumption that all energy and radiation were already known. That single breakthrough unleashed a flood of curiosity. If matter could be pierced by an invisible ray today, perhaps there were other hidden powers waiting to be found. Across Europe, experimental laboratories buzzed. Scientists tinkered with cathode tubes and phosphorescent crystals. They tested all sorts of materials, looking for the next great ray. Some wondered, could there be other forms of invisible energy lurking inside matter itself? Among them stood Henri Becquerel, a French physicist born into a family long devoted to studying light, matter, and their interactions. Fascinated by phosphorescent crystals, crystals that glow faintly after absorbing light, Becquerel speculated, if such crystals can re-emit light after being energized, could they, under the right conditions, also emit rays similar to X-rays? Perhaps hidden energies were waiting inside certain atoms, just waiting for the right conditions. Becquerel gave himself a simple, elegant test. He would expose phosphorescent uranium salts to sunlight, then place them atop a photographic plate wrapped in opaque black paper to see whether the salts would emit some penetrating radiation, like Röntgen's X-rays, capable of darkening the plate even through the paper. It seems straightforward, a modest experiment. A single hypothesis, but the result would be anything but ordinary. In the early 1896, just months after Röntgen's announcement, Becquerel began his experiments in Paris. He gathered uranium salts, known for their phosphorescent glow after exposure to sunlight. He carefully wrapped photographic plates in thick black paper to block ordinary light, then deposited samples of the uranium salts directly on top. Finally, he laid the setup out under bright daylight, confident that if the salts absorbed energy, they might re-emit it as some invisible, penetrating radiation. After several hours of sun exposure, he developed the plates, and just barely, a faint darkening appeared beneath the uranium samples. It was subtle, but unmistakable. Something had passed through the black paper, reaching the photographic emulsion and leaving a trace. For Becquerel, this was no accident. It looked like the birth of a mystery, a whisper of some energy beyond ordinary light. Yet, in the days that followed, fate intervened. The skies over Paris turned gray, the sunlight vanished, and with it, the immediate possibility of more experiments. In February 1896, clouds settled over Paris. No sunlight, no bright daylight to energize the uranium salts. Becquerel set aside the experiment, placing the plates and uranium salts wrapped in black paper into a drawer, intending to wait for clearer skies before continuing. It was meant to be a mere pause, but as days passed, curiosity outweighed patience. On a whim, Becquerel retrieved the plates and developed them, expecting to find nothing, since no new exposure had occurred. What he found instead astonished him. The plates were deeply darkened, showing pronounced silhouettes where uranium salts had rested. How could this be? There had been no sunlight, no stimulation, nothing to trigger phosphorescence. And yet, the photographic plates had been exposed. Something invisible, unexplained, was doing the work. At that moment, Becquerel must have realized that this was no longer an odd extension of X-rays. This was something new, something intrinsic, constant, and utterly mysterious. Becquerel did not stop there. He understood the need for rigor. He repeated the experiment, this time deliberately working in complete darkness, using photographic plates sealed in opaque paper, with uranium salts resting on top. Once again, after development, the plates were darkened. The silhouettes reappeared. The effect was persistent, reproducible, independent of light, heat, or any external influence. Not only photographic plates, but other instruments, such as electroscopes, the devices used to detect electric charge, responded to the radiation. The mysterious energy appeared to come directly from the uranium atoms themselves, a silent emission from deep within matter. What Becquerel had stumbled upon was not a variant of X-rays, but a completely new phenomenon. A spontaneous penetrating radiation emitted by certain elements, a property inherent to the material, not requiring any external trigger. In 1896, when Becquerel presented his findings to the scientific world, he described a new kind of rays that did not cease with the removal of light and seemed to come from within the atom itself. This was not just curiosity, it was the first hint that atoms might not be stable, indivisible building blocks. Instead, they might harbor energy and internal structure, a paradigm shift in how we view matter. Enter Marie Skłodowska-Curie and her husband Pierre Curie, both young scientists working in Paris, inspired by Becquerel's results and determined to dig deeper. Using sensitive electroscopes and painstaking chemical techniques, Marie Curie began systematically measuring the activity, the intensity of radiation emitted by different minerals. She did not chase glow or sparkle. She measured, she recorded, she compared. Very quickly, a pattern emerged. Uranium salts were not alone. Thorium, another element, also emitted the same penetrating radiation. Some uranium ores were far more active than pure uranium itself, suggesting that other, unknown elements might be hiding inside. By 1898, their relentless work paid off. From complex, heavy ores such as pitchblende, they isolated two entirely new elements. First polonium, named by Marie in honor of her native Poland, then radium. These elements were extraordinarily radioactive, emitting far more intense radiation than uranium. Suddenly, what had been a strange, isolated observation was revealed as evidence of a universal principle of nature. Radiation wasn't just a quirk of uranium salts. It was a fundamental property of certain atoms, an intrinsic energy embedded in the heart of matter. The Curies had turned accident into science, curiosity into discovery. With the discovery of polonium and radium, thanks to the Curies, the phenomenon had found a name: radioactivity. A name that would mark the birth of a whole new field, nuclear physics. No longer were atoms considered immortal, unchanging spheres. Instead, they became dynamic, unstable, a reservoir of hidden energy, waiting to be unleashed. The discovery of radioactivity forced a radical rethinking of what matter is and what it can do. For their pioneering work, Becquerel, Marie Curie, and Pierre Curie were awarded the 1903 Nobel Prize in Physics, the first of many honors to come. Through their efforts, radioactivity transformed from a strange laboratory curiosity into a robust scientific concept, measurable, comparable, and ready to be explored. But even with uranium, thorium, polonium, and radium on the table, and radioactivity named, scientists did not yet fully understand what this radiation was made of, or why different substances emitted different intensities. It would take a new generation of physicists to dig deeper, foremost among them, Ernest Rutherford. He began to approach radioactivity not as a curiosity, but as a window into the inner structure of the atom. Through careful experiments, Rutherford concluded that the mysterious rays actually came in different forms. What first looked like a single kind of radiation now decomposed into at least two, and later three distinct types. The alpha radiation, made of relatively heavy, positively charged particles, stopped by a few sheets of paper. The beta radiation, composed of much lighter, negatively charged particles, later identified as electrons, is able to penetrate metal sheets several millimeters thick. Finally, the gamma radiation, a third type of radiation discovered by others, extremely penetrating, similar to high-energy X-rays, capable of passing through most materials. This classification showed that radioactivity was not a simple uniform glow, but a complex phenomenon, with different kinds of emissions, energies, and behaviors. It was evidence that atoms were not solid, unchanging spheres, but dynamic systems with internal structure, a dense nucleus releasing particles and energy. Through this work, radiation became not a lab oddity, but a key to understanding the fundamental nature of matter. The atom was no longer a stable brick. It was a living, changing world. Sometimes, a small, seemingly insignificant moment can change everything. On that overcast day in Paris, a scientist developed photographic plates he expected to be useless, and instead found an invisible mystery imprinted in silver. From that moment came a fundamental truth. Matter was not solid and immutable. Atoms, once thought to be indivisible building blocks, were in fact dynamic entities, full of hidden energy and change. Radioactivity showed that nature had deeper layers, forces waiting to be discovered. The implications were profound. First, understanding the age of Earth and the solar system. With radioactive elements slowly decaying over time, scientists found a natural clock that allowed them to date rocks, fossils, and the history of our planet. Radioactivity also transformed medicine and healing. Once feared and mysterious, it soon became a powerful tool for diagnosis and therapy. From early X-ray imaging to radium-based cancer treatments, radioactivity reshaped modern medicine. Finally, atomic physics and nuclear energy. Radioactivity laid the foundation for understanding the atomic nucleus, nuclear reactions, energy production, and ultimately, the beginning of the atomic age. But this revolution came at a cost. In those first decades, many scientists and workers handled radioactive materials without knowledge or protection. Some, including pioneers like Marie Curie, paid with their health. The same power that healed also carried danger. Before 1896, the universe seemed stable and predictable, atoms fixed, matter unchanging, energy neatly categorized as light, heat, electricity, magnetism. The discovery of radioactivity shattered that calm. Suddenly, matter itself became alive with potential. Atoms could decay, they could transmute, they could emit invisible energy with no outside push. An inherent restlessness at the heart of the material world. Science had to catch up. Chemists and physicists reimagined the periodic table, accounting for radioactive elements and their transformations. Geologists gained tools to date ancient rocks and reconstruct Earth's history. physicians gained new powers to peer into the human body and to treat illness by revealing that atoms were not the smallest, unchanging units of matter. Radioactivity opened the door to a future no one could have imagined. Nuclear physics, quantum theory, nuclear energy, medical isotopes, radiocarbon dating, and more. All rooted in a cloudy day in Paris and a pair of forgotten photographic plates. The story of radioactivity is not one of a master plan or a perfect laboratory. It is the story of curiosity, patience, and humble observation. A few photographic plates, some uranium salts, a cloudy week. A scientist willing to follow his curiosity rather than discard a failed experiment as meaningless. Later scientists, Marie and Pierre Curie, Ernest Rutherford, and many others refined, classified, measured. They gave radioactivity a name, a structure, a framework. They turned accidents into science, curiosity into knowledge, and mystery into understanding. Because of that accident, we learned that the invisible can change our conception of reality. We learned that matter can decay, that energy can emerge from within, and that the universe is more complex than our eyes can see. If this tale has amazed you, remember what it shows. Sometimes the greatest discoveries come not from grand designs, but from small mistakes, overlooked details, and minds willing to wonder. If you enjoyed this story, consider subscribing to explore more origin stories of major scientific breakthroughs. Because history shows again and again, science hides its deepest secrets in the quiet moments, waiting for someone curious enough to ask, what if? We'll see you in the next video.